All right, so we're in the world of sampling now. So sampling is all about how do we make inferences about populations based on samples. So what we're going to look at in this video is weights of apples in an orchard. So our orchard is going to be our population, and the population has a mean, which we'll call mu. There is some real average, I think you would agree, of the weights of apples in that orchard. And that's, so we call that mu, and that's the sum, it's the mean of all the values in the population. The sample mean x bar is the mean of values in a particular sample. So x bar is you've taken maybe 25 apples from your massive orchard and you've calculated the mean of a particular sample. Okay, so all apples weights in an orchard has the population mean, which is mu, and then x bar is our crate of apples that we've taken as a sample so that we can draw inferences about the population average for our apples. So big picture stuff here. The classic one that comes to mind and why this might be useful is Australian elections. The Australian community that's of voting age would be the entire population, but it's unrealistic and it's very labour intensive to survey everyone, which is what has to happen on election day. So in order to make predictions about what's going to happen on election day and who's going to win the election, they have to take samples. And ideally, you take a random sample of the Australian population and then you find out their views on politics. And then once you gather all that information from a much smaller number of people, you can draw inferences about what's going to happen on election day and who's going to be voted in or not voted in. That's sort of the usefulness of this sort of stuff. And so this video sort of hones in on this concept, the sample mean, or the mean of a sample is probably better language, of a normal variable, so a normally distributed variable. So there's a few other terms we need to know, and the terminology in this drives me crazy. So that's in terms of the notation. So x bar varies within each sample. So we treat it as a random variable, capital X bar. And let's have a look at what that looks like. I'll try not to get too sidetracked explaining it because this does a better job of explaining it than me. So basically, a sample size of n is described by independent random variables x sub 1, x sub 2, all the way up to x sub n, with each with the same distribution as x. Because you're selecting apples from your orchard, you're basically saying x sub 1 will have, one of the apple's weights will have the same distribution as the distribution of the apple orchard more broadly, right? So what we can say is we end up with a random variable x bar where we just want to find the sample mean, or this is our sample is made up of these, right? So we take x sub 1 plus x sub 2, so weigh apple 1 in your crate, so this is within your sample, weigh apple 1, weigh apple 2, weigh apple 3, all the way up to how many apples you want to weigh in your sample, and then divide by how many apples you collected, right? And the last thing we say is since x bar is a linear combination of independent normal random variables, x bar is also normally distributed. I think we spoke about this in another video. If you add a normally distributed random variable to another one, you just end up with another normally distributed variable. So we're still getting this sort of nice bell curve shape when we sort of add distributions together. So I think it'll come together a bit when we talk about this specific example. So let's do that. I'm gonna leave this here for you to look at, and then I'm actually going to come back and talk about it in a second because I think the implications of this are more important than the actual the proofs here. So what we have here is proof of expected value and variance of x bar, and remember x bar is our sample that we've taken. So the key insight just to take away from this, which is important, is that averaging n independent values keeps the center at mu, so it keeps the center in the middle, but reduces the spread. And so we get a standard deviation of x bar being the square root of the variance. So the square root of sigma squared on n is sigma on the square root of n, just by taking the square root of this. I'm going to come back and explain this in a second. I actually think this, is more technical and it'll make more sense what's going on here once I explain the rest of it. So let's look at the sample mean. We'll continue to look at that, and let's hone in on our apples, okay? So here's our situation. Maybe you're in quality control, you work for the Apple company, and you're saying, firstly, that your apple orchard, so X without the bar, is normally distributed with a mean of 150 grams for the weight of the apple, and a standard deviation of 15. And so we can pick a crate of n equals 25 apples, like we were talking about. And then our job is to describe the distribution of the crate mean. So how does our crate, what's the distribution of the crates mean? What does that look like? And here's a question to get us thinking a little bit. The first thing I want us to think is, will the mean of 25 apples vary as much as a single apple? And just pause and think about that for a second, because this is, I think, gets to the core of the question here. So you've got your apple orchard. If you were to select a random apple, you could select one that's 190 grams, or you could get one that's 130, so sort of at both ends. But if you were to take the mean of your crate, I think you would agree that if you're taking the average of, say, 25 apples, that it's not going to vary as much. The mean of the crate is not going to vary as much as a single apple would if you just collected it from the orchard. And that should make sense, right? I think that hopefully sounds, clear enough. It's not going to vary as much. So we might get this idea a bit more clear in our head if we looked at this diagram here. So we can clearly see we've got a normal distribution for our individual apples, capital X. This is our distribution, right? We're more likely to find apples with 150 grams to them. We've spoken about this before. Areas underneath this curve represent the likelihood that you'll find apples within those weight boundaries. And so when we actually transform this into the crate mean, that's what the proof showed us. It showed us that we're actually going to get something that looks like this. It gets much narrower, and it's going to look like that. And it should make sense. It's 5 times, if our sample size is 25, we get 5 times smaller standard deviation. So the curve gets taller and narrower, but it still has an area of 1. There's still a probability density function. There's still an area of 1 underneath this curve. So this here, I'll just explain it, is we take the standard deviation, which was 15, and we divide by the square root of the number of apples we selected. So in this case, 25. So we get 15 divided by 5, which is 3. So we end up with a standard deviation, which is much smaller. We had a standard deviation of 15 before, but when we start to look at the mean of our sample, when we look at the standard deviation of our sample, it's much smaller. It's just 3. And again, that should make sense. It's not going to vary as much because your crate, you're going to have, big apples and small apples. They're going to cancel each other out when you sort of calculate that mean. So you'll notice that the mean, or the expected value, stayed right in the middle. And that's what we meant before when we said that the expected value of the sample mean is unbiased. It doesn't get shifted or doesn't change much, and that's why it's used widely in sampling. So the other thing just to mention is that the variance does change. The standard deviation went from 15 down to 3, so it got 5 times smaller when we looked at the crate mean, which we've called X bar, which is also normally distributed. Okay, so hopefully that makes some sense. Let's go back here like I promised and have a look at this explanation. So all we're saying is, what's the expected value of our sample? Well, we defined our sample in this way. We take up all the individual apples in our sample. So X1, X plus, and I found this a bit confusing, so I'll just explain it. X1, because you're selecting an apple from the orchard that has a distribution. But this is sort of describing a process. This is a good way to describe it. This is describing a process of calculating the mean for one of the apples in your crate. So this is basically just, the weight of one apple. You do that 25 times and you find the average. Okay, and here's just some, more sort of abstract things. But basically, we've got a factor of 1 on n. That's allowed to come out the front. So there's a 1 on n out the front of all of these terms. And then, which is what's called linearity of expectation. And then, because we've got n groups of this, we're doing this n times, right? So we're doing this n times. And E of x sub 1, because the expected value of one apple fits the mean of the population, is within the orchard, right? So you get that this is mu. So E of x sub 1, E of x sub I, or any of them, equals mu. Okay? But then you're doing it n times multiplied by 1 on n times mu. Because you can see there's n groups of them, right? You've got one here, and then you've got another one here, all the way up to x sub n. So you've got n groups of 1 on n times mu, which is just mu. So you notice that the expected value didn't change. So let's go back here just to really drive the point home. When we transform to the crate mean, the expected value stayed at 150. And that's what we mean when we say it's unbiased. Okay, the variance, more fun stuff. So the variance of our sample, again, this is the definition. This is what we said earlier. We're adding all the apples up, the weight of all the apples in our crate, and then we're dividing by n. All right. Here, we're taking out 1 on n squared, and I need to really think about why we're doing that. Give me 1 second. All right, so yeah, that's just a property of a variance. So let me just state this clearly so it's clear because I haven't written it here. The variance of Cx is equal to c squared variance of x. So basically here we've got a constant of 1 on n out the front of our distribution here, which is in the numerator. So when it comes out, it becomes 1 squared on n squared, which is 1 on n squared. Okay, and so by similar logic, we've got n groups of adding all this up. All this is saying is the sum of n terms. We've got n groups of, this term, and then we've got number 2, and then number 3, all the way up to n. And then, it's n times 1 on n squared times sigma squared, because the variance is sigma squared. That is what the variance is. That's just the notation we use. Okay, so the n's cancel out, so you're left with sigma squared on n. And so what it's saying is the variation shrinks with larger n. And let's just really, again, come back to that concept. The larger the sample you take out of your apple orchard, if you take, 100 apples instead of 25, you're going to get your curve's going to get even narrower, because your mean of your crate is getting close to the mean of the population, because you're taking more and more, right? So the variation shrinks with larger values of n. And so, that is our proof of expected value and variance for our crate mean or our sample mean. And it's not to be confused with later on, we're going to make some videos about taking multiple samples. And this is where I think I got a little bit, found it a little bit confusing, because we're not taking multiple samples here. We're just talking about one sample. And isn't that just interesting in itself? You can take one sample and you can say straight away that the mean will stay the same, which should make sense. The mean will stay the same, but the variation will decrease significantly, because you're no longer taking from the whole orchard, you're taking the average of your sample, which is going to change your distribution in this fashion. It's going to get taller and narrower, and hopefully you can see why. So hopefully that makes a bit of sense. I think, it's an interesting concept, that's for sure. And good luck with all your studies. If you found it useful, give us a thumbs up and subscribe. Good luck. Talk to you soon.